Exomoons, the next logical step in exoplanet discovery, have been identified in old Kepler data. I'm Matt Miller, you're watching Trekzone, and this is a Talkin' Science Story of the Week.
With the latest science and space news 5 days a week across Apple Podcasts, Spotify, Google Podcasts and YouTube, this is Talkin' Science with Dr. Brad Tucker and Matt Miller.
Alrighty, Brad, our next story of the week. I'm loving this one. Exomoons are now a thing. Not just now, but they've been posited, they've been possibly discovered, and now there's a few more candidates that have been discovered.
We've talked a lot about exoplanets and the planets being found and the diversity range from big Neptune things to Jupiter things to Earth-like things. And one of the big questions is always, we know how common planets are now. What about the moons? We see all of the moons in our solar system. What about exomoons, moons around those planets, around other stars? And a few have been hinted at in the past, and I think there's probably two that are fairly believed to be confirmed, but a new analysis of some of the interesting objects from the Kepler Space Telescope has found probably 6 potential new moons, so definitely boosting the pool of known exomoons.
It makes sense that there are moons out there orbiting other planets, really, doesn't it? Because one of the things that astronomers have been discovering is that our solar system really isn't that unique.
That's exactly right. When Kepler was launched 15 years ago, close to now, the main question was just how common planets are. We didn't know it at the time, and we only knew of a decent amount, but we didn't know the range of stars there around, how many, and those sort of things. When it discovered there's so many, and it is common, as you said, things like our solar system in terms of multi-planet systems and the types of planets are common, then it just kind of, everyone just made sense, like, yeah, there are moons out there. But the trick is, it's hard enough to find a small planet. It's really hard to find a moon around that planet. So you're not going to be able to find all of the moons. You're not going to be able to find the small moons. Things like Mars, not only is the planet hard to find, but the moon is essentially impossible to find because they're tiny. But you can find the things like our moon or the bigger ones around Jupiter, Saturn, or Triton around Neptune.
And to use your needle in a haystack analogy from a few weeks ago, this is like finding a needle in a haystack here on Earth, but instead of being on Mars, you're probably on Pluto.
That's right. And you're trying to look through the eye of the needle at the same time, just to, because you have nothing else to do. And look, you're talking about very, very subtle problems and changes, because, the trick here is what you're looking at is the planet going around the star. And as it goes in front of the star, it blocks some of the light. It eclipses it. Now, what you're trying to do is firstly figure out how often it goes around so you can get an understanding of its period and its distance. But if there's multiple planets, that changes because they're at different distances. So those eclipsings happen at different times and different strengths. So how do you distinguish the multi-planets? So there's just multiple planets in that galaxy, or that star system rather, versus the moons going around it. So you have to kind of time it. So if you do think it's a moon relative going around the planet going around that star, you're going to only see the extra eclipsing of the moon when the planet is near the star. Not always aligned, but pretty close to it. And you're looking for, obviously, very subtle variations in the light curve. And you need to have this happen multiple times to not only confirm it's real, but rule out other possibilities. So it's a really big trick to try and do this. And, a big, remarkable piece of work to find 6 of them.
It is incredible. And thinking that most exoplanets are found using the transit method, as you've talked about, across the star, to think that then you've also got to look at the transiting object to see whether that's doing anything to find these moons. It's just incredible and puts into perspective just how much data is involved in these readings from Kepler. As we've talked about in the past, the project ended in 2018, and astronomers are still studying the data and still finding new stuff to talk about.
Yeah, it's a remarkable data set, and it's why it was such a big mission and changed our view, because it did all that, because of the precision, because of the work. And there'll be more discoveries. And as we find new things or new planets, we'll go back and look at the Kepler data to see if it was there, or, as we discover new ways of finding out or distinguishing between moons and planets, we'll go and look at it, because TESS, as we've talked about, Kepler's kind of replacement, is monitoring some of the same things Kepler did. So we'll have a very long baseline of time, and that is an important thing. The general rule of thumb is you need at least 3 transits to confirm the planet at least. So, if you're something like Jupiter, where you take 10 years to orbit the sun, or, 7 years to orbit the sun, you have to wait 20 to 30 Earth years to see that. You have to wait a very long time. Even Earth, you have to wait 3 Earth years. Mars, you're talking about 5 Earth years to see it 3 times. So you really need to wait and, play the perseverance game and the data collection game and the analysis. So, over time, the rate of discoveries will even increase from what we found today.
And that's very similar to exoplanets, really, isn't it? The rate of discovery of exoplanets, it really has picked up in recent years.
That's right. Perfecting the techniques, the strategies, what we want to look at, where should we be looking at? It's really, the sky's the limit, so to speak, pun intended here. And, and that's kind of the remarkable thing. And, one day we'll be able to, in the future, not this decade, but, look at and zoom in on those moons, just as we've had in our own solar system, to see what they're like, what could they contain, are they similar to some of the very, exotic and interesting moons of Jupiter and Saturn, or are they more boring ones like our moon, or God forbid, Mars's moons, which are just bleh.
They're just going to become a ring system again. Boring.
Exactly. It's going to be a ring system. Come on, you're just a failed moon here.
Well, we've talked about analyzing Kepler data, old data, and finding new things. Hubble's still finding new things. One thing I've never actually asked you, Brad, is just how long after the mission is completed do we run out of things to learn in the data?
This is a good question, because it's increasing with time, in the sense that as the missions, telescopes, or both on the ground and in space, get more complex or more interesting, the discoveries keep happening longer after. And it's really about data volume. So some of the space telescopes, for instance, 20 years ago, they couldn't look as many things in many complex ways. So there's limited ways of reanalyzing it. For some things, if you just need pure data volume, so you just need to look at things for a lot of time over a long period, you'll keep reusing it and reusing it. And this is kind of the way, especially astronomy and space science, is going. There's just so much data pouring in from all the facilities that we have and all the different ways of measuring and observing and calculating that, some people don't even observe or collect new data, because there's just so much out there. You reanalyze with new objects or new findings or new studies or new ideas. And this is, I think, one of the very important part of the community is what we call open access, where just because you built it, make it freely and publicly available. Because you want to do your science, but tens to hundreds of other people will have other ways of looking at it, analyzing it, and it just extends the richness and data of it. And that's part of it too, where in the past, if you took the image, say, 30 years ago using photographic plates, or 40 years ago using photographic plates, and you took a little glass plate of that star or galaxy, only you pretty much just kept it in your office. No one else saw that. But nowadays, it's so publicly available that everyone's like, oh, I've been trying to look for these things, or I was looking at that star and it's here as well. There's just so much way of overlapping that the science is becoming increasing and reusing old data, because we're making it available to use old data. In fact, one of the projects I'm doing right now is digitizing our old photographic plates to link it with our database, the same database that listeners would have heard that big black hole was discovered, we just talked about, from, and finding ways of reanalyzing that. We just have to make it available.
Well, it certainly is future-proofing the industry and allowing many more astronomers and researchers to come up and study. If there are students listening and wondering what they're going to do with life, they have a fascination for astronomy. There certainly is no shortage of stuff to do as an astronomer.
That would be the fair statement of the century, let's say that.
Alrighty, Brad. Well, that is our Talkin' Science Story of the Week. We've got one more to go this week. But for now, thanks very much for bringing this one to us, and we'll catch you on the next episode.
Take care.